we prove a theorem regarding compact spaces, and this is our second theorem about compact spaces. First of all, Introduction to Topology and Modern Analysis is the book for undergraduate students, and this is a very feasible book, and you can find many results and examples on different topics. Today we prove a theorem: any continuous image of a compact space is compact. So let's start its proof. The proof is very simple. Let's suppose that, let me take a map from x to y. Be a continuous mapping from a compact space x into a topological space y. To prove the image of x, which is fx, is a compact space. This is our main aim, that we have to prove that the image of f, which is fx, is a compact space. Note that this image is a subset of y, and the space fx tau is a subspace of y. Where tau is the relative topology on fx. Suppose that the family or class I belongs to I. We take a family of open sets, and we suppose that the family I belongs to I. This is an open cover. Of fx. So if this is an open cover, so then by the definition of open cover, fx is equal to union where I belongs to I, gi. And here I would like to mention again that, like in the previous video, that fx can also be written in this way, that this is a subset of union of gi where I belongs to I. So by the definition of open cover, this holds, and by using this inclusion we can conclude that the equality holds also, that is fx is equal to union of gi, I belongs to I. So first of all this one holds, and by using this inclusion we prove this equality. So you can write uh, either of these things, so it doesn't matter, but basically uh, we write usually in the books, uh, means we means by the definition of open cover we write in this way basically. And if you write in the other way, like fx is equal to union of gi, I belongs to I, then it doesn't matter because this equality is the consequence of uh, the inclusion, that is fx subset of union of gi. Okay, so this equality is a consequence of this inclusion. So but basically, first of all, by the definition of open cover, the authors of the books they write the by the definition of open cover they write in this way. So if this one holds, then this equality holds. But for simplicity and for the for the sake of convenience for the students, uh, you must write in this way because this is very simple. So here now this can be written as 1. If x belongs to x, then fx belongs to fx. This is the capital X, and this is equal to union of gi, I belongs to I. By using 1, fx is equal to union of gi. This implies that fx belongs to gi for at least one I. Actually what we are going to do, we are going to find an open cover for x, and then we apply uh, the assumption that x is compact, then we will have a finite subcover, and then ultimately we will prove uh, the theorem by using all these conclusions. So this fx belongs to gi for at least one I belongs to I, because this is because fx belongs to the union of gi, so it must so fx must belongs to at least one gi. And then gi is gi is an open set of fx, and fx is a subspace. So the open sets of subspace are of the form like this gi is an open set, so gi has the form fx intersection oy, where oy, or you can say oi. Okay, because fx is a subspace of y, so sorry, gi is a subspace of y, then gi is equal to fx intersection oi, where oi is open in y. Okay, so this is by the definition of subspace. Gi which is equal to fx intersection OI, where OI is open in Y for at least one I belongs to I. This implies that fx belongs to OI for at least one I belongs to I, and this implies that x belongs to f inverse of OI for, again, for at least one I belongs to I, and this implies that because this x belongs to at least one f inverse OI, then for all I we can write here x belongs to, when we take the union of all f inverse OI, then f of course belongs to union of f inverse OI, where I belongs to I. So this is the element of x, and it has been sent in this union. So it means that x is a subset of union f inverse OI, I belongs to I. And remember that why this is an open cover, because this union is an open cover for x. Okay, because each OI is open in Y, and we have that f is a map from x to y, which is a continuous mapping from the compact space x into a topological space y. So since f is continuous, so the inverse image of each open set in y is open in x, and since OI is open in y, its inverse image f inverse OI is open in x. So each f inverse OI is open in x. So ultimately these are the open sets of x, and x is the subset of the union of all these open sets. It means that this union is an open cover for x. Okay, and since x is compact, we have, or you can say we deduce like this. So we have, or we deduce that we have that this open cover has a finite subcover. Okay, ultimately x is a subset of union I from 1 to n f inverse OI. Then for all x belongs to x, what will happen? Since X is a subset of this union, it means that every element of X is in this union. So it means that for all X belongs to X, X belongs to at least one F inverse OI. For at least one I belongs to I, where sorry, not I belongs to I, for at least one I where I is from 1 to n. And this implies that fx uh, this implies that fx belongs to OI for at least one I, where I is from 1 to n. And implies that fx belongs to f of x intersection OI, because fx is in the image fx, because this fx is of course belongs to the image of x. So that's why it means that fx belongs to both fx and OI, and hence fx belongs to the intersection of fx and OI for at least one I, where I is from 1 to n. Okay, and this one is equal to gi, because before we have shown that each gi is of the form like fx intersection OI by the definition of subspace, and where we have fx is a subspace with respect to tau, and tau is a relative topology, and the open sets of tau are gi, this one gi, okay, gi are open in fx, and they are equal to, they have the form like fx intersection OI by the definition of subspace, and this one is equal to this is equal to gi. So we write here like gi for at least one I, where I is from 1 to n, and hence fx belongs to union of gi, where I is from 1 to n, because fx belongs to gi, so so ultimately fx belongs to the union of all gi's where I is from 1 to n. And this implies that because for all x fx belongs to union of gi I from 1 to n, it means that it means that uh, it means that all elements of fx, all elements of fx, which is like f of small x, okay, all element, because we have for all x belongs to x, this one holds. It means that what is fx? Fx is an element of fx, so it means that all element of fx belongs to union of gi from 1 to n, and this implies that fx is a subset of union of gi I from 1 to n. So this shows that this union of gi I from 1 to n is a subcover for fx, and this is a finite subcover because uh, gi's are finite from 1 to n. So before we have an open cover like this family, this is an open cover. We suppose that this is an open cover for fx, and we have found now a finite subcover of this open cover, that is g1 g2 to so on gn. This is a finite subcover for the above open cover. So it means that uh, union of gi I from 1 to n is therefore here therefore union of gi I from 1 to n is a finite subcover. Fx. So we have found a finite subcover of fx, and hence we know that hence we conclude that fx is a compact space. Because for every open cover of fx we have a finite subcover of fx. So the continuous image of a compact compact space is a compact space, hence proved. Thank you.